Okay. Hi guys, welcome to the homework 3 bootcamp. So we'll go through I'll go through RNNs and GRUs and then mention we'll go through CTC and Beam search. Did you guys get time to look at the write-up by any chance? Okay, hope this helps you get like an overview of the homework. So just some logistics. The early submission for this homework would be October 31st, and on-time submission is like the final submission is November 7th. And just a reminder, there are no late days that can be used for P1, so plan accordingly. This is a big homework 3 part 1. Okay, so in this homework, you'll be implementing RNN cells, which you have been studying in lectures for this week and the next week as well. Then using the RNN cells, you'll build a simple classifier. So you'll have different layers of the RNN cells. Then you'll be implementing GRUs, and we'll be building a character predictor using GRU cells. The next part of this homework would be implementing CTC loss, which is a kind of loss that we use for RNNs, RNN-based problems. And then we'll implement techniques that we'll discuss today, like greedy search and lean search. So this was the high-level flowchart of this homework, and it is present in the write-ups. Please take a look at it. I won't go into details. This is just for an introduction of different components that I talked about. So we have the input sequence across different time steps. That is X1, that's time step 1 to T. And we will be coding up two types of models, that is RNNs and GRUs. And this basically shows you how they are trained and how the outputs are finally decoded using the techniques. So we'll go through this flowchart again at the end of this presentation. Okay, so a simple RNN is just one block that is applied at every time step, and it takes it in input at every time step, and as well as the previous hidden state. So this is the equation that you'll be implementing for the forward and backward functions of the RNN cell. So in this slide, I've just shown how the hidden state that we study in class is computed. So the xt, that's the input at time t, and ht minus 1 is the previous hidden state. So you have the weights for the input as well as the hidden state, and then you have biases for both. And then you use the tanh activation function. Does anyone want to answer if you guys know why do we use the tanh function and not anything else? Okay, so the reason we use tanh is that it's non-linear, obviously, but it is also bounded between -1 and 1. So due to these bounds, we can mitigate the exploding gradient problem that we face or when the activations are unbounded, like ReLU or sigmoid. One more thing that I want to highlight here is that tanh is centered at 0, which is a useful property for us because this makes the optimization easier. And since we have positive and negative values as well to reduce, which reduces bias and allows gradients to flow like in both directions and not just 0 up. Yeah, I hope everyone is following on Zoom as well. Okay, so this was just the basic RN that you will implement forward and backward. Then you'll use the RNN to build a RNN phoneme classifier. So if this rings some bells, you did a phoneme classification task in homework 1 as well. But this time that you'll do in homework 3P2 as well, the inputs would be dependent on each other, or they would be connected to each other. That's a processing a sequence instead of independent sounds. So yeah, so I like to model it as a many to one task. You are given a sequence of inputs and you are expected to get one output. Okay, so that was RNN cell and RNN phoneme classifier. Then let's talk about GRUs. So you will implement GRUs as well for homework 3. So in standard RNNs, as we just saw in the equation, the long product of matrices, it causes long-term gradients to vanish or explode. So one of the earliest methods that we proposed to solve this issue was LSTMs, that is long short-term memory network. So GRUs, that is gated recurrent unit, it is a variant of LSTM and it has fewer parameters and the performance is good and it is significantly faster to compute as compared to LSTMs. So yeah, you'll be learning this in the homework. So these are the 4 equations that you compute in GRUs, and these 4 equations basically represent the reset gate, update gate, the memory content, and the hidden state computation. So this section would be a lot of would take a lot of time because it involves a lot of derivative calculations. Okay, so here, as you can notice, we are using sigmoid for my reset gate and update gate. So just an intuition why we use sigmoid. Sigmoid is basically limited to 0. Outputs of sigmoid are limited to 0 and 1. So these values are great for us to describe how much information to pass to the next state. Like that is why we are introducing GRUs, because to remove that long short-term memory problem. So the reset gate, the equation is on the slide. So the purpose of reset gate is to determine how much of the previous state, that is HT minus 1, do I have to ignore in computing the candidate hidden state. Then for the update gate, the purpose is to determine how much of the previous hidden state to carry over to the next state HT. So just for an intuition, the output of update gate, that is ZT, would be between 0 to 1. So if it is closer to 1, that means I will retain most of my past hidden state. And if it is closer to 0, then it focuses more on the new input, that is XT. Okay, I hope everything, like the gates, would be more clear to you when you go through the writer. Okay, so as you can see in this equation, the reset gate is applied to this intermediate output by by the element-wise multiplication from the linear combination of the previous and in states. So the reset gate is like a forget gate in the LSTM, if you are familiar with that. So the hidden state is computed as a combination of the memory content NT, of the memory content NT and the previous hidden state HT minus 1. So because we provide you the equations, the GRU forward function should be relatively straightforward to implement, but the backward for GRU will require you to go through a lot of derivative computation. So just some tips for um, Okay. So, yeah, so you are, as we are introducing gating in the network, we just have some tips. This will be the longest question in homework 3P1. And just ensure all the intermediate DWs and DBs are correct. Then we also have a resource, this PDF. We also have it attached in the Piazza post, so you should go through it. And yeah, this is just an example of if you have the function like this, so you should, like, this would be very useful to implement in your homeworks. You don't have to worry about writing the backprop equation for everything at once. You should divide it in these intermediate variables and then take derivative for each step. So here's just some intuition on how to approach the chain rule through element-wise multiplication. So this is an simple example. Let's see the element-wise multiplication of A and B. So this means that A, B, and C will have the same shape. So note that only the elements in the corresponding positions that, let's say the element colored yellow here in the C matrix is only affected by this and this element. So the computation would be very simple for this. So yeah, you don't have to compute everything at once. Okay, so that was for RNNs and RNN classifier and the GRU cell. Now, you will also code up GRU inference, which we call the character predictor. So yeah, so that can be taken as a many-to-many task because you create multiple characters for multiple sequence. And this is a little bit different from the RNN forming classifier. So here, the hidden state at each time step is also passed to the linear layer to predict the character at each time step. So overall in this homework, you would be implementing backpropagation for RNN cells. That would be backpropagation through time for RNN classifiers, and for GRUs, where you would be using gating and chain rule for gated networks. Okay, does anyone have a doubt in this? Okay, let's move on to the next.
Okay, hello everyone. Let's move on to the second part of the homework. The connection is temporal classification, or you can call it CTC. So CTC is a very useful loss function that can help your model training and learning, especially if your input sequence and the output sequence have different lengths, and you don't know the exact fixed alignment between them. Okay. Okay, so this method, in other words, is like to make your model still learning, even if you don't know that which part in your input sequence match the label. And this method is very useful for tasks like speech recognition or like handwriting recognition, because like the timing for each sound or for each stroke is not fixed. So for example, just imagine the spoken phrase hello. So in the audio level, the audio across the time maybe look like this. Can you see my mouse? Give me a second. Okay, so for example, the audio across time is like this first line, hello. So it has the length like the length of 10. But our target sequence, hello, only have the length of 5. So you can see that the input sequence is much longer than the target sequence. This is where the CTC can help your model learning. So the CTC can help your model automatically find the best alignment between your longer input with your shorter target sequence. I will explain to you how it works later. And in this way, you do not need to like label by step by hand. Okay, so we will implement these ideas in our homework under the CTC directory. We first extend the target sequence with blanks, and then we calculate the forward and backward probabilities. Then we use these forward and backward probabilities to get the posterior probabilities. And then we finally calculate the CTC loss based on all of that. So let's see the first step, extend the target with blank. So why we want to do this, as just shown before, the input sequence is always like much longer than the target sequence. And it's often that the input sequence do not have the fixed alignment to your label, to your target sequence. So this is why we want to first extend our target sequence with blanks. So here, the blank is defined in the initialization of the CTC. The blank gives your model flexibility so that the model can just predict nothing between your different letters. And in this way, the letter can just stretch across multiple time steps without forcing into one-to-one alignment. And also, when you just add a blank, you can also help to separate the repeat characters in the words. For example, like in this word, it have 2E in this target sequence. So when we add the blank between them, we will just prevent this 2E being merging into only 1E at the end. And here is a visualization to like how the final extended target sequence looks like after we add the blanks. Also, the CTC allows for the skip connection. So this is defined where the model can just skip the blanks. For example, so the one here denotes the position that where the model can where it can allow for skips. So that means the blank that at that position at the right before this one can be skipped. For example, for this one, it's at the fourth position, and which corresponding to this E in this extended sequence. So that means this blank before this E can be skipped. So your model can just move it from this B directly to this E without this blank. And it's also same for this eighth position one. So that means this F position, so this blank before this F can be just skipped. So the model can just move in from this E directly to this F without this blank. But you have to be careful if there's some repeat character in your word like this 2E in this target sequence, this blank cannot be skipped. Otherwise, these two E's will be merged into one E at the end. Okay, after we extended the target sequence, let's see how we calculate the forward probabilities. So the forward and backward probability together led us to compute the total likelihood of the correct alignment, that making sure to including all the possible passes through which the input sequence could generate the target output. So let's first look at the forward probabilities. This is written as alpha t comma r, and you can see that so this t denotes the time step t in the input, and this r denotes the position in the extended target sequence. So this alpha t comma r tells you how the probability that this model get from this time zero step to this time step t to reach to this symbol r, the probability of this process. And this figure that just give you a visualization of this process in more detailed way. So you can see that all the red arrows in these figures denote all the possible paths that you can pass from the previous symbol to the next symbol. And when you calculate the alpha t comma r, you have to consider all of these red arrows to this time step t. For example, you have if our t is at this time step 3, so you have to consider all these red arrows before it. So you have to add up all this probability of these red arrows. It's just this part. This alpha t minus 1 comma q is the previous state of your model, and then you have to multiply the yt here. It's also here. So this yt means the probability that your model just predicting this symbol SR at this time step t. And after that, you have this alpha t comma r. Okay, so this is the figure that from the write-up. It's a dynamic program table of the forward algorithms. So in this figure, each column denotes a specific time step from t equals to 1 to t equals to 6. And each row denotes the position or symbol in the extended target sequence, like this way. And for each cell, it's denoted as the alpha t comma r. This storage is the probability that the model gets to this symbol at this time step. For example, at t equals to 1, so we first initialize our probability with the first non-blank character, which here is a b. And then we keep all the other values to 0. And when the time goes on, the forward probability just propagate forwardly. So you can see that's this way. And then at the end of this table, we will consider all the passes that can that through these passes that our model can based on this input sequence to get this output sequence. It add up all the possible probability of across all the passes. Okay, let's move on. So after calculating the forward probability, let's see how we calculate the backward algorithms. So our forward algorithms is calculated like from left to right, but backward algorithm is calculated reversely. it calculates the probability from right to left. And it is denoted by the beta t comma r. This represents the probability of generating the rest of the sequence starting from the time t. For example, previously we calculated forward path. Let's say our time t is at this rate. And then for now, we will calculate this backward path. This blue area. Okay, so this is very important. So very important to tell us how we can, the probability that we get to this future state from this current state. And as this equation shows, so it feels like sum of all the future states that come after your current states. The beta t plus 1, consider your based on your current time state t. And then it will multiply with this yt plus 1. It's the probability that your model predicting the next token at this next time step. And also you may notice that there will be some difference between this backward algorithms equation compared to the forward algorithms. So here at this backward algorithms, we just consider this future states and multiply with this yt plus 1. But in the forward path here, we consider the previous state alpha t minus 1, and we multiply yt. This is the probability that the model predicting the current state. So personally, I think this is because the forward algorithms move from left to right. And so at each step, we look one step earlier. This is t minus 1 in the forward path, and multiply by the model's prediction at the current time. This is the t. But for the backward algorithms, this does the reverse way. So it moves from right to left, and it looks one step ahead. So it's t plus 1, and then it will multiply by the model's prediction at the next time step, t plus 1. So I know that this part may be a little bit tricky for you to understand, but in short, you can just grasp all of this process in this way. So the forward path is like to sums over all the previous states. So it's like we're moving from past to the present. But for the backward path, it's more like that we sum over all the future states. So it's like we're moving from present to the future. Oh, and also we will just provide some pseudocode in the lecture slides. So you may want to just refer to this pseudocode when you implement these homeworks. Okay, after we calculate the forward and backward probabilities, let's use them to calculate the posterior probabilities. So for the posterior probability, it means the probability of being in the state R at time t, given the input sequence. So here in the numerator, it's like the multiply of our forward probability and the backward probability, alpha multiply beta, and then we normalize it with the sum of all the alpha multiply beta. So just to be note, the difference between the numerator and the denominator. So in the numerator, we only consider the model that gets to the symbol R at this time t. But in the denominator, we sum over all the symbols. just do not restrict only this R. We sum over all the R, symbol R, to normalize this numerator, so that the full value will be a normal probability that can add up to 1. Okay, once we know this probability of posterior probability, we can just use it to calculate the CTC loss. So here, these formulas just give you an idea how you can just get the posterior probability and plug it into the loss function. So this first equation is just shown before. It's how we get this posterior probability. And then we just plug this posterior probability into this loss function. So we first take the minus log YT. This is a probability that the output of our model at the time step t. And then we weighted this log YT, minus log YT with this posterior probability, and we sum over all of them to get the overall loss. This is a loss value that our network wants to minimize through the training. And look at this derivative as a side. So this derivative tells you how the loss value changes with respect to each of your model's output YT. And this is a derivative that our model uses during the back propagation part to update your gradients. Okay, so as long as we calculate the CTC loss, the CTC loss only gives us a probability distribution over the possible alignment, but it does not directly produce the final output sequence. So that means we need a decoding strategy to transform our model's output into meaningful text. There are two main ways for this. One is graded search, and the other is beam search. In this homework, we will let you to implement both of them. So for the graded search, just as the name suggests, it's very simple and straightforward. We just pick the highest probability token at each time step. For example, in this figure, we just choose the top probability symbol at each time step. You can see this blue framed block at each time step. And then we just combine all these chosen symbols to get this final output back. But before we output this sequence, we have to first delete the blank in this sequence. Just delete them. And also we have to combine the repeated letters, these two ways, so that we can get this clean version back at the end. So graded search is very straightforward when you implement in the homework, but sometimes it can miss the overall better alignment because it's only consider the top probability at each time step without considering future probabilities. So to improve on the graded search, we introduce the beam search. Instead of just consider only the top probability at each time step, we keep track of the top k subsequences as the model moves through time. So in this way, the model can consider like multiple promising paths so that it will have better chances to find the overall better alignment. For example, in this figure, the leftmost node is our start point. So our model is trying to just predict the symbols as usual, like blank A, B, blah, blah, blah. And for each symbol, it has their own probability. But just different from the graded search, here, we do not only just keep the top probability of the symbol, we set the k equals to 3, for example. So we keep the top 3 subsequences at each time step. For example, at t equals to 1, we keep this 3 symbol because this 3 symbol is the top 3 probability subsequences. So we get that blank A, B as this time step 1. And then for each partial path, we can just expand them by adding additional characters as you run, like this way. Each can be expanded by adding new characters. And also, we only keep the top 3 subsequences. So you can see that we, at time step 2, we still only just keep the top 3 subsequences. So just repeat this again and again. At the end, we will have the 3 subsequences that have the top 3 probability. And our model will just choose the subsequences with the greatest probability as our final output sequence. So when you just go through this process, you can just have the sense like the beam search can be much more computational expensive than graded search. But in general, it can give you better results than graded search because it like balance the exploration and the probability. Okay, again, here is a flowchart of our homework 3 P1. We just want to give you a high level of what happened in this homework and also give you some ideas like when you just finish each blocks, like finish each files, how you can just interact or combine your your blocks to have your own model training. But we also want to know that. So in this flowchart, the testing process of your homework 3 P1 may not exactly like this process. It's just that we want to give you some ideas how you can implement all of these blocks and how these blocks can interact with each other in some more actual real problem ways. So here we have the input sequence across time. And then we have these 2 models that you have implemented before, that each time I have introduced to you before. So first we have this RNN phoneme classifier. It's like mapping to 1 map. So at last we only have like this only 1 prediction per sequence. And then we have this another model. It's the GRU inference that you have implemented before. And then it's different from this classifier. It's like many to many map. And then we can just use this model's output as the input of the CTC loss. What I just mentioned or introduced to you before, the CTC process. And also then you can use the CTC decoding strategy like graded search or beam search to decode your model's output to get this final predicted output sequence. Okay, that's all from our homework 3 P1 part. Any questions so far? Okay, cool. We will then pass it to homework 3 P2.
Hi guys, so you can stretch for 3 or 4 minutes. So everything has been released on Piazza, where you will submit your final submission, where you will submit your checkpoint submission. The checkpoint notebook is there, the student notebook is there, even this write-up that you're seeing, it's there. The deadline for checkpoint is October 31st, as you can see here. The checkpoint is worth 10 points as usual. The total assignment is 100%, but the checkpoint is 10% of 10. It's 10. So if you don't submit the checkpoint by this time, you're going to miss 10 marks. This is not an early submission, this is checkpoint. So you have to actually submit so that you get the full 10 marks. So what the checkpoint notebook entails is that you should have met a distance. So as you can realize, for homework 2P2, you are testing you guys on EER, and we're asking you the lower the EER, the better for you. This is the same case with homework 3. We are checking what we call the Lewis-Time distance, and I'm going to explain in a moment what this distance is. And for the checkpoint, it's 12. And you should be able to get to 12 even with the basic architecture that will give you on the notebook. So if you can manage to implement the basic architecture that's in the notebook, you should be able to get these 12 with no issues. Then from there now the patterns will be released, and then you need to do the extra, read some papers, modify your architecture so that you improve your level instance. Again, so that's the first thing for the checkpoint. You need to get a score of 12 or lower in Kaggle, and then the homework quizzes. So if you go to the checkpoint notebook, you have a couple of questions for you guys to answer, and with the questions you can always get all of them. What you can do is just you can submit to checkpoint as many times as possible until you pass all the questions. So you send question 1, you see if you are passing, and then you maintain the answer of question 1, and then you do question 2, which will be pretty easy for you to pass. So the MCQs are in the checkpoint, and then so that's it. Checkpoint, you get 10 over 10. Then the final solution is November 7th. It might seem far, but it's around the corner. So I encourage you to keep working on the homework so that you finish this as soon as possible. Then after this, November 7th, we shall release the final homework, and that would be the end of the planning, and that would be the end of this semester. So we are closer to the end. If you have made it this far, congratulations. Then after November 7th, we expect you guys to clean up your code over the weekend, and then you generate the submission on Sunday. That will be November 9th, and it's pretty simple. The last few codes on the student notebook contains an already implemented function for you guys. You just need to fill your details like your Kaggle username, your 1DB, and then the path to your notebook. What you normally encourage people when you're generating submission is you move your code to Colab because it doesn't require GPU. It's just some basic things. So please join the Kaggle link. It's here. When you click it, you can join. And I mean, this is the only way you can join the Kaggle link. If you have multiple Kaggle accounts you're using to train, and then you want to test your scores and everything, you should always come back and click this particular link so that it can lead you to the competition. So that's it with the logistics. So we are going to start the things about this homework. As I told you, it's similar to homework 1 P1 to some extent. The parameter limit, just like homework 1 P1, is 20 million. This is not an intensive network. It's not like homework 2 P2, just really complicated. This should be pretty easy. Testing is just like 2 or 3 minutes per epoch. It's not like homework 2 P2. So if you actually put in the work right now, you might even pass the check or the high cutoff before you even release them. And then, so what's the objectives of this homework? Over the past few lectures and the upcoming lectures, probably 2 more, you guys have been learning about RNNs, GRUs, LSTMs, and this will lead you to encoders, decoders, and then finally transformers, which will be the epitome of this course. So this homework is designed to test you or to help you learn more about LSTMs, GRUs. And the good thing with this, you can also use the CNN that you learned in the previous few lectures to implement this model architecture. So you'll actually see it will give you better performances. You can even also use ResNet in this particular homework also. So if you had a chance to read the ResNet paper, it's better for you. CTC laws, in turn, I talked about it in homework 1P, in homework 3P1. The one that you'll be implementing from scratch, you can also use it at this particular homework, and it's actually pretty easy. Yeah, so it's basically LSTM that we want you guys to learn and how to go around in the LSTM. Yeah. Another thing, you'll realize that you can also use attention in this particular homework. Homework 4, you'll be using attention. So don't rush into it. Leave attention for homework 4. I'll assure you, if you use attention in this homework, you'll even I don't know if there's like index 0 in the leaderboard or something will be up there. So please don't use attention. Just stick to the LSTMs and the CMUs and the resonance. Yeah, so the checklist, as I told you, this homework is pretty easy. It's just a bunch of things we want you guys to do. Learn how, just read a documentation online about LSTM or something, packing, padding, and then you should be good to go. We will want you guys to implement the training and evaluation loops. You guys have been doing this from homework 1P2 and homework 2P2, so it's something that you should be used to. You should also build a feature extractor, and as I told you, MLP for the final layers for classification. You guys have been doing this, so it's not something new. It should be pretty easy. And the most important thing, remember to win at life. So if you can't win in this particular homework, wherever you will go, just ensure that you win. Yeah. So we are moving into the executive summary. As I told you, it's LSTM. It's really nothing much. So the main thing that I would like you guys to learn is the Leverstein distance. What is the Leverstein distance? This is what we'll be using to judge your score in Kaggle. So if I ask you to say the word hello, okay? There will be a way you'll say hello, and then there's the actual way hello is written. So if there's a way your model will predict the word hello. Let's say it will miss the first character. Instead of hello, it says yellow. So we'll compare the two words. Then the Leverstein distance is the distance at the minimum number of changes you need to make from your prediction to get to the actual prediction. So if the actual word is hello and your model predicted yellow, you will realize that you'll only need to change the Y alone, okay? But if your model predicted yearly or something, you'll realize there's a lot of things you need to change from your model prediction to get close to the actual prediction. So are we clear on the Leverstein distance? It's just the minimum amounts of changes you need to make from your model prediction so that you get close to the actual prediction. So that's what we'll be judging you in your case. So you realize that the smaller the distance, the better for you. That's why the score is now descending. You are not looking for the highest Leverstein distance. You're looking for the smallest Leverstein distance. Okay. So I think you're clear on that. Hints for better performance. We have given you just use two BLSTMs. You guys, we need you to go and read more on this. Like homework 1 P1, homework 1 P2, we encourage you guys to use frequency and time masking augmentations because this homework is pretty much the same. One might actually say the data set is the same, but I'm going to tell you in a moment why there's just like little bit of difference between homework 1 P2 and homework 3 P2. But time and frequency time masking will still work on this particular homework. So once you have been able to pass the distance, the 12 distance for the checkpoint, you can come back to this particular section and see the things we recommended for you guys to try, go and read, and then you implement them in your papers. That's okay? Good. So the data set, like I told you, homework 1 P2 and homework 3 P2 is kind of similar. So what you are doing in homework 1 P2, if you don't remember, or if you are by coding, we were giving you frames and phonemes, okay? And in each frame, we had a label for it. So if you actually go back and study your data, you can actually see that each frame had a label for each data. So if we have like 100 frames, and what do I mean by frames? The way I'm speaking right now, we can break my words into frames. So each frame can be given a label. So if it's a word like, you can see here, if it's this kind of this wave, it can be broken down into frames. So the first part was Y, the second part is E, the second part is S if you are trying to pronounce the word yes. That was for homework 1 P2. But for homework 3 P2, it's a sequence to sequence. So you have the entire number of frames. So it could be 100 frames, but you're only giving you 4 phonemes. So if you're trying to pronounce the word hello, so I can say hello, and someone else can say hello, and someone else can have like a higher intonation. We will pronounce the word hello differently. So what you need to recognize is that all these people are trying to pronounce the same thing, okay? And the name, okay, the labeling for this particular number of frames is just hello. So if we break down your hello, into 100 frames, and we break down my hello to 50 frames, but you're all pronouncing the same thing. So what am I trying to say here? The number of frames, not each frame has a unique label. Hope I'm trying to make sense there. Yeah. So it's a sequence to sequence. You have a high number of frames, but few phonemes. So you need to figure out. So actually, seeing the problem there is that if we have 100 frames, H, if you're saying hello, could have covered only the first two frames. But someone who's saying hello, you realize that H can cover a number of frames. So the question we're asking ourselves is, we want to label these frames, but H covered how many number of frames? Is it 2? Is it 3? Is it 4? That's like the main backbone of this assignment. So we are trying to now find out this first, if the word is hello, H, it covered how many frames? And then he, it covered how many frames? Then L, it covered how many frames? And then you also see that L appears twice in the word hello. So you're asking yourself, the first L, where did it start? Where did it end? And then where did the second L start? And then where did it end? So that's this data set. Yeah. So you'll realize that, yeah, of course, you're not going to be implementing this out of scratch. There are specialized loss functions for this particular homework to help you implement whatever I'm telling you. So if you go and read into the CTC, like you see the one I've underlined here, you can see there's a way. I mean, you're not the first people to encounter these problems. People have been building speech models from time before, and people have come up with optimized ways of solving this. So if you go and look at the CTC, you can actually see there's a way they have implemented, and it will help you in your homework. Yeah. And even you'll be implementing CTC also in part 1. So it kind of builds you up and, tries to get you excited in all of this. Yeah. So this, what you see here is what I was telling you. The way a person can say yes and the way another person can say yes is different. So the question is, where does this start and where does it end? And is it this that is elongated or is it the first while? Yeah. So I think that's it with the data sets. So and then again, I'm coming. Yeah, so what are we asking you in this particular homework? Find out where the frame starts, find out where the frame ends in a high level sense of it. Yeah, so that's what we mean by an alignment problem. Okay, what I've been explaining is what we mean in the write-up as an alignment problem. So there's 2 ways we can go about this, just to kind of give you a high-level overview again. We're breaking our problem into two steps. We call it an encoder, and then a decoder. Let me show. Let me just go down here. So what you're going to do is, in basic English, we have 26 characters, right? So we are going to say in every time step, okay, we know that you're trying to pronounce the name. Let's use an example like the word yes. We know that you're trying to pronounce yes. So our vocabulary has 3 phonemes, Y, T, and S, okay? So in every time step, you're giving the probability of, okay, what's the probability that this word is a Y? What's the probability that this word is a EH? And then what's the probability that this word is a S? And then in all the time frames that you have, you predict. Okay, so this is the first time frame. What's the probability that's a Y? What's the probability that's a EH? What's the probability that's a S? Go to the next time frame. What's the probability that's a Y? What's the probability that's a EH? What's the probability that's a S? You go through all the time frames. Then at the end, there's a couple of ways you can do this. You can just go in every section and pick the highest probability. Okay? And that's in the code, how to calculate the probability and everything. I want to believe you've been learning about what the algorithm and everything in the classes, and even in the write-up, it's there. So the first thing you can do what we call a greedy search. You just go picking the highest probabilities. But then at some point, you'll realize that this is not actually always the best option. So the next thing is, so let me just, so let's not lose the high level picture. The high level picture is when you want to label these frames. Okay? And the way of labeling these frames is by giving it probabilities in every times if your language, if your vocabulary has only 3 letters like YE, has only 3 phonemes like YE, S, that will be the probability will be assigned, and it has to add up to 100. So you'd say Y, the probability of the first letter being Y is 70, this other one is 15, this other one is 15. It should be able to add up to 100. If your vocabulary contains 100 words, you need to assign every word a probability. So the first way you can go about this, you can go after labeling all these frames. It's in the architecture. After labeling all these frames, just go picking the highest probability. But this is not always the most optimal way. So that's what we call go to yeah, so that's what the Viterbi algorithm does. It kind of assigns the probabilities. So you can either do what you call greedy search algorithm, saying, okay, I've done my part, I've assigned probability to all these frames. So let me go just picking the maximum probability and say, okay, this is what my model is trying to say. Or there's what we call beam search. From the word beams, it's like you're just sending a couple of beams. You're looking back. So instead of picking the highest probability in every frame, you can pick the k-best probabilities, okay? The top k. So if your vocabulary is a vocabulary of, let's say, 40 phonemes, for example, in this example, you pick, so in your notebook, you will see that you have given you 3 as the beam parameter. So you pick the top 3 probabilities, and then you cast them to the next layer of frame. So your model will always be looking at the last 3 beams. So like you see, I've drawn them here. So it will be looking at the last 3 beams, then it will be saying, okay, these are the ones that are kind of leading me to the word yes. Because you realize that the word yellow is a little closer to hello than, let's say, willow or something like that one. Yeah, so I mean, ideally, the point I'm trying to pass here is that you can either pick greedily the top probability in every frame, or you can look back at the top k probability frames from the previous time step. Yeah, you guys, when you read the write-up, well, you will kind of understand what I'm trying to tell you. And I want to believe even in classes, Prof has talked about this being such. But that's ideally what we want you guys to implement. So from what I'm telling you, you can decide to implement greedy search algorithm in your notebook, but it won't give you like the best results because it's just greedily picking frames. So the best that we want you guys to do is beam search, and again you'll be implementing beam search in homework 3 P1, and then you can always move that beam search in homework 2 P2, homework 3 P2, and it will still work. Yeah. So the note we are telling you here is that the beam that we have given you is 3. We don't want to have like a high, we don't want you guys to be looking at a lot of beams from the previous probabilities. A lower beam is best 3 or 4 or 5. Yeah. So there's one thing I've not talked about. So you will realize that the lengths of these frames are difficult. If we pass a batch to a network, the way you are saying hello, again, we are going back to our example, you can say hello in 100 frames, and I can say hello in 30 frames. You will realize that if you are passing that batch size into our model, deep learning, the input is always of a fixed size. Okay, we are expecting an input of, let's say, 512. But then your hello is it's 200, and then my hello is 100. So you'll realize that there's something the input to that in that particular patch size is not aligned. So what you normally do is you pad. So the box here, let's say it's just different people saying hello. So you'd see this person said hello in 7 frames. Then this person said hello in 4 frames. Then this person said hello in 6 frames. Then this person said hello in 5 frames. But this is a batch size that you are passing into our network. And our network takes in only fixed size. And our network always refers to the batch size for the input size, okay? for when you are passing data into the model, it looks at the input size of the byte size and says, okay, this is my input size that I'll be taking for this particular byte size. If the next byte size comes, it also looks at that byte size, what's the input size. So if you're sending a byte size like this, you'll quickly realize that we'll have different lengths of the incoming data. So what you normally do is that we put these zeros, okay? So for every incoming byte size in your data loader, when you guys will be designing the byte size, what you need to do is, okay, this is the incoming byte size. What's the longest number of frames in this particular byte size? Once you have gotten that longest number of frames in that particular byte size, pad the other data points in that byte size to be equal to the longest one. Are we clear? So again, where are we processing the byte size? We are processing the byte size in the data loader. So you ask yourself one question. There's an incoming data set. I mean, the data set is huge, but your model can't take the entire data set at one time. So you need to batch them and then you send them to the model. So for every single batch, look at the set of data points inside this batch size. And then you ask yourself, what's the longest one in this batch size? And then you add the other sequences, add other data points to be equal to the highest data point in that particular set. Yeah, so like we told you, in homework 1, you are doing a frame classification. This one, you're doing a sequence classification. In homework 1P2, every frame had a label. In this particular homework, you have many frames, but the labels are just one. Yeah. So a few seconds ago, I was talking to you guys about padding, and then further details about padding, you'll find them here. You can pad with anything. You can pad with X, you can pad with 1, you can pad with 3, just ensure that the padding number should be constant across all the byte size. And we recommend you guys to pad with 0. Yeah. So this is what I was telling you. You see, we are padding. Just introduce a bunch of zeros there. Yeah, so on the evaluation, I was telling you guys about the Levestein distance, and here is the explanation. We are trying to find the word party, but our model predicted park, okay? So the Levestein distance here on a high level should be 2, because why? We need to remove this K and then fit it with T, and then there's a missing character we predicted here. So that's ideally what the metric we're using to judge you guys. So like you can see, the left hand distance is 2 because we need to do 2 operations. Yeah. I think I talked about the checkpoint submission, the on-time submission, and just to go through the logistics. If you pass the high cutoff, you get 90/90 plus the 10 that you had in the checkpoint, you already have your 100 in homework. If you get a medium, so if your score is between 70 and so when we release the cutoffs, let's say the Levestein cutoff is 5 for high, and then the medium one is 7, but you're somewhere in between the 7 and the 5. We just do linear interpolation. You can actually calculate it yourself before you submit. Just if 5 is equal to 90, what about 7? Yeah. So like, just to reiterate here, we interpolate linearly. So it should be something you should be able to do. Again, at the end of the homework, November 7th, we shall release a Slack day. That's a Slack competition that will run for 10 days. Hopefully, okay, if you have not used your Slack days for homework 1P2 and homework 2P2, you can use all your Slack days here. If you have used your Slack days, just keep count of the number of Slack days you have already used, subtract them, and those will be the remaining Slack days you guys will use on the Kaggle competition. It will be released immediately. The main competition ends on November 7th. So there being no other thing to discuss, congratulations for making this far, and good luck in homework 3P2. Yeah, we just have an appendix of things we thought can be helpful for you here. You can go and read later on. Any questions? Okay, thank you. That's been my time. That's a summary of homework 3P2. My parting shot is that the epochs for this can be done within 2 or 3 minutes. So you can even tune 200 epochs or something. If you're sharp enough and your good work ethic, you should be done with this homework by this week. Congratulations. Thank you. Yes.
I know we cannot use intentions, but seeing some reason stuff about like career transform something to change the use career transformation, or they will be considered as related.
That's a good question. Fourier transform, the question I'll ask is, should you be applying it in a data set or in the architecture?
I think in the architecture, I think.
Yeah, so I don't have an answer to that right now. Probably should post it on Piazza and then we shall follow up and tell you if it's actually an allowed method or not.
Okay.
Thank you. Any other question? Avoid attention, guys. I know attention is all you need, but avoid it. Okay. So good luck. Thank you.